Assalamu alaikum students. Welcome back to seismology. We are having our week number 12 and lecture number 6. As you all know that in our previous lecture we discussed the subduction zone and the earthquake intensity. So let's talk a little bit about the magnitude now. So with the introduction of recording equipment or instruments that could record earthquakes and measure earthquake ground motions, we didn't need to rely on subjective descriptions of earthquakes as much anymore. Instead, we could measure the energies ourselves and be a lot more objective. So seismologists began developing different measure scales to describe the size of the earthquake based on what they were reading on their instruments. So magnitude scales were developed to describe the size of earthquakes. Now there's lots of different magnitude scales. There's not just one magnitude scale, there's different magnitude scales. We are going to talk about these beginning with the Richter magnitude, or the local magnitude is more accurate name, the surface wave magnitude, and then the body wave magnitude, and then finally we have the moment magnitude. Richter local magnitude, so everyone refers to the Richter scale. This was a magnitude 6 on a Richter scale. So you have probably heard people say things like that. That's one of my biggest pet peeves. Okay, no seismologist uses the Richter scale anymore. Nobody uses it. The only thing we use from the Richter scale is the fact that he used the number scale from 0 to 10. And that is the magnitude that we report today, have nothing to do with the Richter local magnitude. The Richter local magnitude was developed by Richter in 1935, and it was based on the measurements that you would get from a Wood-Anderson seismometer. So a Wood-Anderson seismometer, this is a little picture of one down here and one on the bottom right. It's just a basic pendulum based device that where the mass would move, that moving mass was attached to a pin, and it would then record or scribble a line on a piece of paper, and then based on how much that mass moved, you know, it would determine the amplitude of the line scribble, and then you could get how the size of your earthquake there. There were lots of problems with this method, and it's probably one of the biggest reasons we don't use it. I mean, first of all, Richter developed it only for Southern California earthquakes. That would be, and Anderson seismometer was calibrated just for the earthquake in South California. So if the earthquake occurs anywhere else, they were different. It didn't really work. It does not distinguish between waves type, that mass that's on that would Anderson seismometer moves, regardless of whether you have body waves or surface waves, P waves or S waves, or any of those. Okay, it basically doesn't distinguish between the waves types. The other thing that's really interesting, it's really sensitive to periods up to 0.8 second of vibration. And what this really means is that happens to be the period range of the instrument itself. Every object, I don't care what it is, every object has a natural period or a natural frequency of vibration. And if you rattle something or shake something at its natural period of vibration, it will rattle itself to pieces. The Wood Anderson seismometer has a natural period of vibration for periods less than point a second. And so the earthquake motions less than zero point 0.8 seconds really got into going. And then the other thing was it's saturated at magnitudes greater than 6.5 to 7.0. And that would look like it's let's see here an earthquake size, all actual earthquake size or energy is this right here, and here is the local magnitude on the y-axis. What we would see is that as earthquake local magnitude would grow, as well as it will grow together until we have a certain size. It would level out and it was saturated, and that size happened to be right around about 6.5 to 7 or so even if the energy was much greater than 6.5, it was still registered as a 6.5 or 7. Some of students have asked me why that occur. I don't really have an answer why it saturates. One seismologist told me once it's because that the mass of the seismometer was hitting the side of the box and couldn't move any further. I don't know if that's true, but it still makes me laugh thinking about it. So anyway, students, that's the Richter local magnitude. I hope you never make the mistake again of saying to referring to the magnitude of an event as the Richter magnitude, because it's just not accurate. Another magnitude scale is called the surface wave magnitude. It's labeled as m sub s, being for the surface wave. This is based on the amplitude of Rayleigh waves with a specific period of 20 seconds. Okay, so the period of the wave is 20 seconds. Now this magnitude scale is based on displacements of not the acceleration of the ground, which is kind of interesting here. The equation to compute the surface wave magnitude, where A is the maximum ground displacement from the Rayleigh wave of a period of 20 seconds, and it's in unit of micrometers. So we are talking really small displacements. Okay, and then this capital D or delta, okay, right here, it's referred to in literature as the epicentral distance, because it's not really a distance, it's an angle. What angle is it? Well, if you draw just two-dimensional representation of an earth like this is shown right here. Imagine the earthquake happening somewhere and draw a straight line to the core of the earth, and then from the core straight up to your recording station. That the angle that is formed, that angle is delta. That's the epicentral distance. That's not really a distance, it's an angle. Okay. Uh, well, there were problems with the surface wave magnitude as well, because it's based on the surface waves. It's not really built to handle deep earthquakes that are governed by the body waves, not the surface waves, or it's not built to handle earthquakes that are closed. And by closed, I mean generally I'm going to say less than 50 kilometers. And earthquakes that are close, they are about 50 kilometers. Yeah, surface wave, it is terrible. And why is that? Well, because body waves are what's reaching your instrument, not surface waves. And then, like we saw with the local magnitude, we would get saturation in our magnitudes at about 8 to 8.5. So we can read energies up to 8 to 8.5 on a scale, but anything greater than 8 or 8.5, it will max out, and we will never calculate a number greater than 8 to 8.5. Okay. Well, if you have a surface wave magnitude, then you need to have a body wave magnitude, and we do, and that's labeled with an M with a little sub b there. And this is based on the first few cycles of arriving P waves to the instrument. So it's not based on S waves, it's based on P waves. And so those compression body waves, this is much better suited for the deeper earthquakes or earthquakes that are really close to you. Here's the equation for it, where A now is the amplitude in your instrument from the P wave arrival, and it's in micrometers. Then we have T, which is the period of the P wave. So it's going to usually be around 1 second, but of course, you are not going to guess that. You are going to measure it from your recordings, and that is before the delta. This is the epicentral distance, which really isn't a distance, it's an angle. There are some problems with the body waves magnitude. First of all, it's not really suited for large shallow earthquakes. Those are the types of earthquakes that are better for our surface wave magnitude. And then it saturates and saturates at a magnitude of 6.5, which is kind of thinky, not really fun. So it's a problem with all these different magnitude scales, and then they saturate. It's good for small earthquakes, but for large earthquakes, you can't really accurately characterize the amount of energy that's there. And so this is what seismologists said: we need a better way, and they develop a better way. It's called a moment magnitude. Moment meaning it's based on the seismic moment. Remember, what we talk about computing the amount of energy released by a rupturing earthquake, or the amount of work performed by the earthquake. So moment magnitude looks like this. This is an M with a W subscript. Not sure why it's W, but we use it. The interesting thing is it's not based on any single instruments. It's based on computation of the seismic moment. It is most commonly used magnitude scale among scientists and seismologists today. So, and here's the equation for it. It's simply the logarithm of the seismic moment divided by the 1.5 minus 10.7, and that's it. And simple. And you have to remember that the seismic moment is going to be in units of Earth. Earth are also the same as dying centimeter. Okay, so there is a lot of advantages to this that we will talk about, but most of the significant one is it does not saturate moment magnitude, has no saturation. It will go all the way up to 10. So if you need it, this is the magnitude that we use today. And if you ever hear a magnitude that's reported on the news after an earthquake or the year the US Geological Survey talking about a magnitude, is the moment magnitude. But it's always mistaken by the media for the Richter magnitude. Okay, so most of think of it is the Richter magnitude, which this is not. So we can estimate the amount of energy released from an earthquake using surface wave magnitude or moment magnitude. But let's go ahead and use moment magnitude. Let's compare the amount of energy released from a magnitude 6 event with the energy released from magnitude 8 event. Okay, so here's the equation we are going to use now. You are going to look at this and say, where did I get this equation? I'm going back to this slide. It's just an equation for moment magnitude, but all I'm going is recognizing the equation to solve for the seismic moment. Okay, so that's all I'm doing. So let's go ahead and do the calculation. So energy is essentially just the seismic moment. So we are going to solve for m0, and if I plug in 6 for my moment magnitude like this, I will write here and I run the calculation, I'm going to get 1.12 times 10 to the 25 ergs of energy. That's a lot. That's a lot. Now if I do the same calculation for the magnitude of 8, I get 1.12 times 10 to 28 ergs. So the difference between these calculated energies is the difference in energy released from a magnitude 6 to a magnitude 8. So if I just divide the two, I get 1000 times more energy in the magnitude 8 event. Then there isn't a magnitude 6 event, which makes sense, right? To go from a magnitude 6 to magnitude 7 is 10 times. They go from a magnitude 7 to magnitude 8 is then we are going to multiply that by 100 times. So 10 times 100, I get 1000, because it's a logarithmic scale. That's how they work. Okay, so let's compare intensity versus magnitude. What if you are dealing with units of intensity we have to remember that it's subjective. It's not based on any measured number. It's based on our perception of shaking and a set of descriptions that are provided. It can vary based on location, just depending on where the shaking is the most intense. It requires a survey of people. Generally, though, there have been studies in recent decades that have correlated intensity back to measure ground motions from instruments. In that instance, that it's not really subjective, but it was intended to be a subjective measure from it. We can produce, I saw sizable maps, and it is strongly influenced by local site condition. On the other hand, magnitude is an objective measure of earthquake size. It is a constant value independent of your location. It doesn't matter if you are standing right over the focus of the earthquake or you are on the other side of the world, the magnitude of the earth is the same. Why? Is because the magnitude is just in a constant measure of the energy released by the earthquake. It has nothing to do with your location relative to the earthquake. It's the amount of energy released by the earthquake. Intensity depends on your location relative to the earthquake. Okay. Magnitude is calculated from instruments. We don't have a map because it's just a single value. It doesn't change depending on where you are, and it's really independent of any local site conditions. So one question that I always like to ask: let's imagine that you and your colleague or your friend are visiting some hilly area in Pakistan. So one of you is standing on top of a tall building, the other of you is out visiting some beach or some seaside, and you are standing on a rock out in the middle of the bay, and an earthquake happens. Okay, and are each of you going to feel the same intensity from the earthquake? Think about it. So if your answer is no, then you answer correctly. Each of you is going to feel a different amount from the earthquake, because each of you is standing on a different medium. One of you is on the rock and the other is on a tall flexible building. The shaking you feel is going to be different because the two of you. Next question will be: each of you experience the same magnitude of earthquake. So think about it. So if your answer is yes, then you answer correctly, because the magnitude is not dependent upon your local site conditions. It's not dependent on where you are relative to the earthquake. Magnitude is constant for a given earthquake event because it is an objective measure of the total amount of energy released by the earthquake. So that was all about the earthquake's magnitude. So in this lecture we study about the earthquake magnitude and discuss different scales. So you guys go through it. If you guys have any questions, you can find me here through this email. You can email me. Thank you so much. Thank you for the participation in the class. Take care.